Okay guys, just welcome to lesson 8. In this lesson, the lesson is titled Graphs of Vertical Projectile Motion. So that is what we're going to be talking about. And for our learning objectives for this lesson is that at least by the end of this lesson you should be able to identify and graph and sketch vertical projectile graphs. So that will be the time versus the position versus time graphs, the velocity versus time graphs, as well as the acceleration versus time graphs. But before we go anywhere, I would just like to acknowledge the copyright. So this is not my thing. This is taken from Science Clinic. It's their summary thing for grade 12 that helps you prepare, and you can actually visit their website and everything else at scienceclinic.co.za. So we have to acknowledge that copyright because it's not our own, otherwise we would be accused of a crime. So let's say now, so the first thing to note in terms of these graphs is that you should know that the position time graph here, we're going to change in y versus a change in t, is a parabola. Remember from mathematics we studied parabolas. So you can see it's almost like you a person who's sad and makes like a face down C or a face up C. So it's a parabola. And then the velocity versus time graph is now actually a straight line. We are all familiar with a straight line. This is a negative, this one has a negative slope and this one will have a positive slope. And then the acceleration versus time graph is just a vertical line, a horizontal line, because remember what is happening is that because these are projectiles, they are moving only under the influence of gravity, and they are moving at an acceleration of g, which is 9.8. So that is why, and it's constant, that gravity is constant throughout the motion of this projectile. So that's why that graph is like this. So after maybe 5 seconds it's still 9.8, 10 seconds it's still 9.8, and 15, just like that. But now the important thing here that if you pick the upward motion is positive, remember I said you have a choice. It's either you can say down is positive or up is positive. So if you say up is positive, then your graphs are going to look like this. And you see that because acceleration is always acting downward, that gravity is always acting downward, the value, that graph is going to be just below the change in t-axis. So that's why it's negative. But if you select up as negative and down as positive, you see that graph actually, that 9.8 is actually going to be above this axis here of the time axis. Now it is positive. So that is something that you have to take note of. So I'm trying to see if I've kind of mentioned everything. So now let's move on to the next page. So now we have various situations described for us here. The path of a projectile. So here they said up is positive, and then point of release is a reference. Okay, like I've mentioned, this is copyright, it belongs to Science Clinic. Okay, so now let us consider this. Let's say there you are standing on top of a cliff, and then you drop a ball from a certain height. Maybe here this will be point C, and then there at the bottom will be point F. You release that ball at an initial velocity of 0 meters per second. So before it drops, it was stationary, and then it will hit the floor just a split second, milliseconds before it actually reaches the floor. It is having a velocity of VF. So this is how we would draw the position time graph. So we have our change in y on the y-axis and then the change in t in the x-axis, and you see this graph is like half of a parabola. So it's almost like a parabola, but only half of it is showing. And then this is how you would draw the, what do you call this, the velocity time graph. So the velocity time graph, you see that the initial velocity is actually there because it's 0. So the initial velocity of this graph would be 0. Let me try to what is it, zoom this. So you see that there, okay, so the velocity of this graph here, initial velocity is 0, and then it will reach a final velocity of f there. So its velocity is moving downward already, so that's why it's moving from 0 to negative, because the velocity is moving downward, and we said downward is negative. Remember, we said the up motion is positive, meaning the downward motion is negative. And then essentially this is how you would then draw the the acceleration time graph. So because the like I've already mentioned, the up motion is positive, this means that our graph here would actually be negative just below that the change in time axis, or the time axis there. So that will be like negative of 9.8. But now let us say scenario 2. Let us say then now the initial velocity is not 0. So you can see, so vi is not equals to 0 meters per second. So this means that the position time graph remains the same. It still looks like what you call this thing, it still looks like half of a parabola. And remember, and our reference point is the point of release, so we still assume that at that initial point there, the change in y, the yi, or the initial point of release, is 0. So, and then it reaches the floor at a velocity of vf. So this is how that graph looks like. You should know this. And then because its initial velocity was not 0, it's not gonna start at origin like this one. It's just gonna start below origin, and because it's moving downwards, its velocity is going to be negative. That's why it starts there, just below the x-axis, below the time axis, and it starts at a certain negative initial velocity, and then the acceleration curve is still the same. But now let us now consider a different situation. You are no longer throwing or dropping the ball. You're no longer dropping the ball, but what you're doing is you're throwing it up, and then it will now come down. So you're dropping it, and then it will travel back down, and then you release this ball at an initial velocity that is not 0. So it's moving at a certain initial velocity, and because it's going up, this initial velocity will be positive, and then it reaches a maximum height here. There at that point, okay, I can actually highlight at that point there, it's the maximum height is at the maximum height, that value will be 0 meters per second, and it's still up. And then now it reaches maximum height, travels down. When it travels down, the moment it travels down, that velocity changes, and then it reaches the floor at a velocity vf, and it's down. So this is how the position time graph would look. This would be at the point where you release your ball, and then this is where it will reach its maximum height there at the peak, and then finally return to the same point that you released it at. So this would be here, and then because you're not catching the ball and it just drops to the floor, this now will continue down up until it reaches here. It reaches the floor. And then this is what the velocity time graph would look like. So this will be the initial velocity. We know that it's not 0, so it is, and it is moving up, so it's positive. That's why it starts on the positive sign. And then when it reaches maximum height here, the velocity is 0, and then it will reach here, maybe the same point that it was released at, and then reach the same velocity, and then finally here, this would be its final velocity when it reaches the floor. Okay, so now let us consider another option. So now we have a graph. In this graph, you throw a ball or any object, and then you catch it. So you don't let it fall to the ground. So this is that position time graph, you see it's a perfect parabola because it does not even go down. So this is what it would look like. This is the initial position where you're releasing it, when it reaches the maximum height, and finally when it returns to the same point when you catch it. And this is what the velocity time graph would look like. So now I'm thinking you are seeing how this graph actually goes. Let me go up, and then this would be the acceleration time graph. And then here it's a different situation again. In this situation, you are actually standing at the bottom of a house, and you throwing a ball up, and then it goes, reaches a certain maximum height, and then drops at the roof of this house. So now this is in this graph, a position time graph. This is where you're releasing the ball. It reaches its maximum height there, which is a velocity becomes 0, and then it drops. But then it doesn't return to the same position as it was released, because it was released at this position, and then it just lands on the roof. And this is what the position of the velocity time graph would look like. So this would be the initial velocity, which is positive when it reaches its maximum height, and the velocity just before it lands on the roof of that. So you see that this velocity will be lower in magnitude than this velocity at which it was released, and here it was released at a velocity that is not 0 as well. And now an interesting situation here, and we're going to do a question, an exam question about this. This is when an object is thrown up from a height and it bounces. I like this one, I don't know why, but in the next lesson I'm going to be doing a question regarding this. So here you are, you throw a ball, let's say a tennis ball, from a specific height, and then you drop it, and then it goes, you release it, and then reaches a maximum height, it goes down, and then now maybe it comes, what do you call this, and then here it lands on this thing, I don't know what you call it, and then bounces. Instead of just landing on that thing, it bounces, and then it bounces back, and then it reach a second maximum height, and then finally hit the floor. So how do we draw a graph like that one? The position time graph would actually look like this. It would look like two parabolas. So for the first one, for the first bounce, no, for the first time that you're dropping it, and then this will be the first bounce. So here you are, you release the ball at point A, it reaches a maximum height at point B, and then there it returns to the same point that you released it at, and finally drops down. And then this is where at C, this is where it actually hits this thing here on the house, and then bounces where it travels back up, and then it reaches another second maximum there at D, and then finally it drops down to the floor. And now, interestingly, look how the velocity time graph looks. So this would look like a number of straight lines. So this is, so from here to here, from A to C, it was just representing this motion here, and then from C to D, you represent that motion there. So it's like two straight lines, and then you have to draw this dotted line. So you're saying, okay, this ball was released at a certain velocity at A, reached its first maximum height, and then finally traveled down, and then was in contact with a certain surface there, and then it bounced back. When it bounced back, it left at a certain velocity, and that velocity here towards the first bounce, there it is, it's positive because it was going up, and then finally here it reaches the maximum height for the first bounce, and then now only travels down to reach the final height. So now this is how you would then normally draw the where am I? Okay, so this is now how you would just normally draw that acceleration due to force by a surface bouncing, and just take note of that. So that discrepancy there when it bounces, because it's not for that moment it's in contact with the surface, or it's in contact with the floor, there's actually no what you call, there's no there's no acceleration. So for that moment, we call it contact time, there's actually no acceleration. So that's why there's that little bit of thing there. Let me read what is it that they're saying here. So they're saying that if collusion is perfectly elastic, so both our momentum and kinetic energy are conserved. So this is collusion. This is a collusion. When it bounces, or when it hits this surface, it's a collusion. The downward velocity before the bounce and the upward velocity after the bounce is equal in magnitude. But this is not a perfect. This is not a perfect. What you call? This is not a perfect. This is not an elastic collusion, because you see it hits the floor. The magnitude of this is of this velocity here is definitely larger than the magnitude of this one. And then let us now wrap up our lesson quickly. This is where now they are talking about bouncing, and balls that are bouncing. It can be a tennis ball. So you see that this moment here, this separation, it's contact time. So imagine you drop a tennis ball for a few seconds. It's actually in contact with the floor, so nothing is happening, and then it bounces back up. So that is what we call contact time. So yeah, this brings us to the end of this lesson. So please be able to draw these graphs, look at this document, and analyze it, so that you are able to draw all of these graphs. You are able to also identify them, without too much trouble. Thank you so much for watching, and we will meet on the next lesson, where we do a question on vertical projectile motion.